Today's lesson, we're going to continue looking at the ideal gas law, but we're going to spend some more time looking at some more challenging problems involving the ideal gas law. And we're going to derive it to help us solve for things like gas densities and molar mass and tie it in with some other types of problems that you may find familiar from other parts of the course. So first, let's do a quick reminder of what density is. Density is equal to mass over volume. Depending on what you're looking at, the mass and volume can have different units. But if we're dealing with the ideal gas law, if we're dealing with moles, we know that's in grams, so grams, and volume should be in liters. So our density here, volume, should be in liters. So what do we know about density, the ideal gas law, and moles? So our first formula we know is the ideal gas law. It has moles in it. We know moles is equal to mass divided by molar mass. And now we have density is equal to mass over volume. So if we wanted to make a quick substitution and start to include mass and molar mass in our ideal gas law, what we can do is replace the moles in the ideal gas law with mass divided by molar mass. So let's first work that out. So here's our ideal gas law. So instead of N, I'm going to put in mass divided by molar mass. Since the R and the T are in the numerator with the mass, you can just extend your line there. So here, now you have a formula that you can use and rearrange to solve for different things. Mass or molar mass. Let's say you wanted to rearrange this for molar mass because there's often problems involving molar mass. You could move molar mass up to the numerator and pressure and volume down to the denominator, essentially switching these two groups here. So you could have molar mass is equal to mass times the gas law constant times T all over pressure times volume. So this is another way to rearrange the ideal gas law that can be very helpful. We'll see how that might help us out a little bit later on with some more complex problems. But what if we wanted to take this a step further and try and include density now? Remember, density is equal to mass over volume. So here, when I look at my equation, I want to get mass in the numerator and volume in the denominator. I already have my mass in the numerator here, so I'm not going to move it, but I'm going to try and get rid of these variables from it first. And then I'm going to move my pressure away from the volume at some point. So let's start rearranging. Let's get rid of the other variables around M. So I would have PV, if I'm going to bring my molar mass, it goes from denominator to numerator. And then I have mass here, but I also want to get rid of R and T. So R and T is going to go from numerator to denominator underneath here. If I want density, I need mass and volume. So I'm going to move now the volume away from all these other variables. It's going to go from left-hand side to right-hand side, numerator to denominator. So I would have M over V. And then I'm going to keep my other variables where they are. And I know M over V is density. So PM over RT is equal to density. But to put this in proper format, I like to have my unknown on the left. So density is equal to pressure times the molar mass over my gas law constant times T. So by playing around with our ideal gas law formula, you can see that you can get a few other formulas in there that can help you solve for different things. Molar mass, density, even this formula here Could help you solve for the mass of something if you wanted to rearrange it in proper formula format. That could also help you solve some variations on some problems. So knowing how to play around with the ideal gas law can be really helpful in some situations. If you don't rearrange them, you can still solve the problems, but it'll just often take you a couple of extra steps. So if you want to add these manipulations to your repertoire of formulas, that would work. Or if you have a kind of a study sheet going, you might want to make one for all the formulas and variables that you see in this unit because there's a lot of them. So now all we're going to do is try a bunch of different variations on some problems involving the ideal gas law that might include density, mass, or molar mass, or a combination of the three. So this problem says, what's the density of 1 liter of carbon tetrachloride vapor at 125 degrees Celsius and 112.4 kilopascals? As we always do, let's write down our variables. We have a volume of 1 liter, a temperature of 125 degrees Celsius, and a pressure of 112.4 kilopascals. And we want to know what the density is. If they're asking you for density, remember density, you need mass over volume. Here there's no mass, but there's a volume given. So you can use one of those manipulated formulas from the ideal gas law. Even though it doesn't explicitly say mass in the question, if they're asking you for density, it means mass. And anytime there's anything involved with mass, you're going to use something with the ideal gas law because it's the only gas law that you've seen that includes mass as one of the variables or variations. So if you look back at the manipulations that we just did with our formulas, there's one that helps us solve for density. Density was equal to pressure times molar mass over our gas law constant times temperature. Now you might think we don't have the molar mass, but secretly you actually do. Since we know this is carbon tetrachloride, you can calculate the molar mass of carbon tetrachloride. 1 carbon plus 4 chlorines. And then you can use that in your formula. Pressure here has to be in kilopascals, which we have. Our gas law constant, we know 8.314. And temperature has to be in Kelvin. This isn't in Kelvin. So why don't you pause the video and see if you can try and do these two conversions, Celsius to Kelvin, find the molar mass, and plug it in to solve for density. So give that a shot and then we'll walk through the answer together. All right, let's take a look first at some of these numbers up here. So this should be 398 Kelvin if we convert it to Celsius to Kelvin. And our molar mass should be about 153.81 grams per mole. Again, it might vary slightly depending on your periodic table that you're using. Now that we have all of those variables, we can start to input them into our formula and solve. So 112.4 kilopascals times our molar mass. And we're going to divide it by the R value. And yep, there is a lot of units here. And then times the temperature. All right, let's look at how the units cancel. Numerator, denominator. Then we've got moles, moles, Kelvin, Kelvin. Okay. And then when we take a look at what's left, we've got grams over liters, which is exactly what we want for density, mass over volume. We need to round this question to 2 significant digits at the final answer. So when we plug all of this in our calculator, you should get 5.2 grams per liter. So that gives you one example of a problem involving a variation on the ideal gas law. Let's try out another more challenging problem. Then I'll give you some hints there with the steps. A compound's composed of 24.27% carbon, 4.07% hydrogen, and 71.66% chlorine. If 1.71 grams of the compound is vaporized and it occupies 519 milliliters at 102 kilopascals and 95 degrees Celsius, what is the molecular formula of the compound? Now you might notice right away by reading this question, some of it sounds familiar. Do you remember empirical and molecular formulas back from one of our earlier units? Hopefully you do, because most of this question starts off with this. So let's start looking at the question together. The first part of the question, you're going to have to find the empirical formula. You're going to do that with this first set of data. Assume 100 grams, find the moles, divide by the lowest number of moles, and get your empirical formula. The second piece of information you would normally need to find the molecular formula is the molar mass of the molecular formula. But here you don't have it. Here, they're giving you information about the compound, its mass, volume, pressure, and temperature. So instead of like the other problems that give you the molar mass of the molecular formula, here you're going to have to do that yourself. How you're going to do that? You're going to use the ideal gas law. Now, which ideal gas law? Remember that variation we just looked at? You want to use the one where you're finding molar mass. So you can have the molar mass up here and pressure and volume down below. Once you've done that, the last step is finding the multiplier, which is something that you have done before. The multiplier is the easiest step. And in case you don't remember, multiplier, you're going to take the molar mass of your molecular formula and divide it by the molar mass of the empirical formula. And then you'll be able to get your molecular formula. So now that you know the 3 steps, what I'd like you to do is pause the video, give yourself a good 5-10 minutes, and see if you can solve this problem. It's a good challenging problem to see if you remember concepts back from Unit 3 and tied in with what we've learned in this unit, Unit 5, with gases. When you're ready to check, we'll take a look at the answer step by step together. Okay, so this was our formula, or sorry, this was our problem. These were our steps and our formulas. So now what we're going to do is start to solve. First one, step 1, we want to find out what the empirical formula is. So make sure that you assume 100 grams, change all of the percentages into masses, and then you're going to convert them into moles. Once you convert by moles, you're going to take the lowest number of moles and divide everything by it. The chlorine and the carbon are approximately the same. And when you do that, you get a ratio of 1 to 2 to 1. So the empirical formula here for your compound is CH2Cl. If you want right now, because you know you're going to need the molar mass, you can also calculate it, which is going to give you 49.48 grams per mole. The next step, if you haven't tried, try it now. is to find that molecular formula, molar mass. Normally, again, that's given in the question, but this time you're given data with the ideal gas law, so you want to do that. So remember we had our formula here, ideal gas law with molar mass on the bottom. The easiest way is to rearrange it like we looked at earlier. So you're taking the mass times the R value times the temperature and dividing by pressure and volume. Make sure you do these conversions. Volume was given to you in milliliters. It has to be in liters. And also temperature. Temperature, make sure that you converted it to 368 Kelvin. Once you have everything in the right units, it works the same way. Plug in your values, and here you should get a molar mass. Remember, this is the molar mass of the molecular formula, 98.83 approximately. Once you've done step 1 and 2, the last step is the quickest and the easiest, the multiplier step. So we're going to take our molar mass we just calculated and divide it by the empirical formula from step 1. And you should find that your multiplier is approximately 2. 98.83 divided by 49.48, you can see it's about half. That means multiplier is 2, so your empirical formula has to be multiplied by 2. So down here, your molecular formula is C2H4Cl2. This is a very challenging problem, so if you found it a little bit tricky, don't worry. But come back and take another look at it after the lesson. If you need to go back and review molar, molecular formula, molar mass, empirical formula, any of those things, that would be something good to do. Now, if you're looking for a challenge or just another type of variation, you can try problem 3. Problem 3 says you're a scientist and you isolate 2.09 grams of a gas. Your sample occupies a volume of 751 milliliters at 88 degrees Celsius and 99.7 kilopascals. You know the gas is either oxygen, nitrogen, neon, or krypton, and you want to figure out what your unknown gas is. Here you are again going to have to use your ideal gas law formula, but again it's going to be a variation. Here you've got mass, a volume, a temperature, and a pressure. So here you want to look for a variant of the ideal gas law with mass in it. So here's some hints. This is normally our ideal gas law. The only way we can get mass in is if we substitute something in for moles, which means mass divided by molar mass. When we do that, if we look at the variables that we're given, we have mass, we have volume, we have temperature, volume, temperature, we have pressure, we always have R, so the only variable that we don't have here is molar mass. So what if you use this formula to solve for the molar mass? If you know what the number is, could you figure out if it's oxygen, nitrogen, neon, or krypton? Think about that, pause the video, and let's see if you can determine the identity of the gas. Give yourself some time to solve the problem and think about it. When you're ready to check your answer, unpause, and we'll walk through the rest of the answer. All right, so again, if you haven't tried this, please try it. It's always better if you give it a shot on your own. Even if it's not always the right answer, it's always a good idea for you to try. So, like we showed up above here, we want to use this formula because we have all of the other variables given to us or available. So, if we rearrange that formula, we're going to get the variation here. Molar mass is equal to mass times R times T over P times V. Then we can start plugging in our variables that we have right into the formula. And you should get a molar mass of 83.78 grams per mole. Now, if you got this far and you weren't sure what to do next, if you have a molar mass for the gas here, what you would need to do is then compare it to one of the 4 molar masses of the gases that were listed above: oxygen, nitrogen, neon, or krypton. You can look right at the periodic table for those, or you can calculate them if you need it. But you have that information even though it's not given to you. With your periodic table, you can determine it. So if we looked at the molar masses of all of those gases, oxygen, neon, nitrogen, and krypton, which one is the closest? You can see that our calculated value is extremely close to krypton. So based on that information, you could assume that the gas is krypton. So hopefully after today's lesson, you are able to look at the ideal gas law from a new perspective, look at some ways to manipulate the ideal gas law using other variables, and are able to solve some more challenging problems.